you ever went to the post office, taken a number, and then waited so long that you have to check your watch over and over again? Long waiting times do not only affect customer satisfaction, but they also increase operating costs for service organizations. This is where queuing theory becomes very useful. We are from RCDCS 1435B from course QMT342. For our group project, we selected question 3, which involved a post office in a small town. On a normal working day, customers arrive at the post office at an average of 5 people per hour. There is currently only one service counter, and it takes approximately 10 minutes to serve one customer. The server working at the counter is paid by RM 8 ringgit per hour. In addition, the manager has to pay another 3 ringgit per hour for each customer that are waiting in the queue. This means that the longer waiting times will increase the total operating cost of the post office. Due to the long waiting time, the people in the town have requests to the manager to open another one more service counter. However, opening an additional counter will increase the cost server. So, the manager needs to decide whether this option is economically worthwhile.
This problem is related to the topic queuing theory. The definition for queuing theory is the study of waiting lines where customers arrive, wait for service, receive service, and then leave the system. There are five main components usually in this queuing system, mainly arrival process, service mechanism, system capacity, queue discipline, and the number of servers. In the given scenario, people arrive at the post office at an average rate of 5 people per hour. Arrival rate follows a Poisson probability distribution. This means that the customers arrive randomly and independently without having any ties with other customers. The service time is given as 10 minutes per person, which is equivalent to 6 customers per hour. Since the service time follows a negative exponential probability distribution, the service times are random but have a constant average rate. For the number of servers, initially the post office has only one counter, which means that the number of servers is 1. This shows that initially the post office follows a MM1 queuing model, but when an additional counter is added, the number of server turns to 2, which means that the system now follows an MMS queuing model. For the queue discipline, in the question, it is stated that customer takes a number and wait for their turn. This shows that the type of queue discipline in the post office is a first come, first served queue discipline, which is the most common assumption for a queuing model. For a queuing system to be stable, the arrival rate must be less than the service rate. In this particular question, it is stated that arrival rate is equivalent to 5% per hour and the service rate is 6% per hour. This shows that the arrival rate is less than service rate. So we can conclude that the queuing system for this post office is stable.
Okay, now let's take a look at the calculation. First, we define the parameter of the system. The arrival rate 5 customer per hour and the service time is 10 minutes per customer. We need to convert the service time into hour. So we get 60 divided by 10 equal to 6 customer per hour. And the number of server is 1. Next, we need to analyze the system with one counter. We are going to use single channel queuing model MM1. The server utilization is given by rho equal to lambda divided by mu. Since rho is less than 1, then the system is stable. After that, the average waiting time in the queuing for MM1 model is calculated using standard formula, which is WQ lambda divided by mu multiplied by mu minus lambda. So now we substitute lambda and mu in the formula. After substitution, we obtain the average waiting time in the queue is 0.83 hour. Next, we calculate the cost for this model. First, list the cost we need to know. The first one is the cost of customer waiting is RM3 per hour. We define as CWQ equal to 3. Then we need to know the server cost is RM8 per hour. We define as CS equal to 8. For the total cost, we use this formula. Total cost equal to S multiplied by CS plus lambda multiplied by WQ multiplied by CWQ. Then we get the total cost for one counter is RM 20.45. Okay, now we analyze the system with two counters as suggested. We use the same arrival rate and service rate, but the number of server is now 2 because they are two counters. Now we use multi-channel queuing model MMS. Since the S is larger than lambda over mu, then the system is stable. Using the MMS formula, we can calculate the average number of customers in the queue we define as LQ. And LQ equal to rho multiplied by lambda over mu square multiplied by P naught and divide by S factorial multiply 1 minus rho square. After that, we are going to use the probability that the zero customer or units in the system we define as P naught. P naught equal to 1 over summation of 1 over n factorial multiplied by lambda over mu to the power of n plus 1 over s factorial multiplied by lambda over mu to the power of s multiplied by 1 over 1 minus rho. Before that, we need to calculate the rho using formula lambda over s multiplied by mu. Then, we substitute the value. We get rho equal to 0.417 and P naught equal to 0.412. Now, we substitute the value we get in rho and P naught inside LQ formula. After substitute, we obtain LQ equal to 0.176. We use the same cost of customer waiting and server cost. Now we calculate the cost of two counter using formula S multiply CS plus LQ multiplied by CWQ. The total cost for two counter is RM 16.53.
For decision, we know that the total cost with one counter is Rm 20 ringgit 45 cent per hour, while the total cost with two counters is Rm 60 ringgit 53 cents per hour. Then, since the total cost with two counters is lower than the total cost with one counter, opening an additional counter is economically beneficial. Based on the decision, the following consequences can be observed by opening a second counter. The average waiting time in the queue will reduce, enabling customers to be served faster and with less congestion. This improvement leads to a more efficient service system and a better overall experience for customers. In conclusion, by applying queuing theory concepts such as MM1 and MM2 models, waiting time analysis and cost comparison, the manager should open an additional counter at the post office.